Okay, so in the previous video, I introduced a continuous random variable. So the important point is a continuous variable has zero probability at a point. So we have to think about inequality, probability defined by an inequality. So we are going to think about cumulative distribution function. And from here, I will show that cumulative, if you know the cumulative distribution function, actually you can calculate any probability, right? So as an example, I will consider uh, x, random variable x, which is the amount of total size coffee. If you order a coffee, then how much it actually contains is x. And for simplicity, I'll assume that you know the CDF at 3 points, right? If you input 11.9, then it returns 5%, which means it is the probability that the coffee contains less than 11.9 ounce, right? And if you enter 12, then 30% is the output, which means the total size coffee containing less than 12 ounces is 30%. And finally, 90% of total size coffee contains less than 12.2 ounces, right? So it should increase because the interval increases from 11.9, 12, and like 12.2, like that. So literally probability accumulates as you increase the input. And here, the problem with the cumulative distribution function is that it only tells you about probability smaller than something. Probability smaller than 11.9, 12, or 12.2. But then how can you calculate probability greater than? Yes, we can actually. So think about this. How can you calculate probability greater than 12 based on these three information? The idea is we know probability smaller than 12, 30%, then automatically probability greater than 12 should be 70%. Okay? So this is like if you think about length, that is like natural. So we know the length from the left up to a point. But we are interested in the length from that point to the right side. We know that. Like because we know the total length should be always 100%. That's from the probabilities basic property. We know the total length is 100%, and we know this much, then automatically you can tell the other probability. That is 70%. Okay, so even though the cumulative distribution function contains information about smaller than or equal to something, that is sufficient to calculate probability greater than something. Okay, by simple like a transformation. Then how about an interval? If you are interested in probability between 11.9 and 12.2, how can you calculate that? Right? You guess it, and my intuition is, again, you can think about the length from the starting point up to 11.9 is 5%. That is our length. And also from the starting point to 12.2 is 90%. But we are interested in like this much. Like from 11.9 to 12.2. How much is that? You can subtract the small length from the full length. Then you get the difference. Like this. So we are interested in probability between x and y is greater, then the CDF at y is length from the smallest point up to y, and CDF cumulative probability at x is from the starting point up to x. And their difference, the red, should be the probability in between x and y. Like this. Okay? So, in our example, the probability should be 85%. It is, again, pretty intuitive if you take if you understand the probability as a length and just think about different points and how to calculate the length, then you are going to get these straightforward results. And it also tells you that cumulative probability tells you directly what is the probability smaller than something. But also, we previously learned, it also tells you what is the probability greater than something. And finally, you can calculate probability between 2 points. So, cumulative distribution function tells you anything, any probability. You can calculate any probability from the cumulative distribution function. That is why we start from the cumulative distribution function here. Okay. Now, so far it was just for like a warm up. It's not general enough. Frankly, it was not rigorous. I explained that the probability is proportional to the length, but actually it was not, because if you calculate the probability, so we have 3 points, so you can calculate probability between the first 2 points and the later 2 points, last 2 points, and you can calculate their probability like this, but it's not proportional. The first interval is half of the second interval. The length of the first interval is half of the second interval. It is the length of the first is 0.1 and the second is 0.2. So the second one must contain twice more probability than the first one. But they are not. What's wrong? Nothing is wrong. The numbers are correct. But what is wrong is because the probability may not be proportional to the length. So just as an example for just explanation for educational purpose, I started with an assumption that the probability is length. It is not so much wrong, but it is not general enough. So we are going to generalize the framework using this idea. So think about dimensions, right? So you know, we are living in a cube, like 3-dimensional space. That is, we have width, height, and depth, right? So you see, like there are 3 like measures, and using them we can calculate volume. But if you reduce it to 2-dimension, it's literally 2-dimensional plane space, and you can think about a square with a width and height. There is no depth, right? And then its measure is area, how big the square is in 2-dimension. In 2-dimensional space, just area stands for the measure, how big the object is. But in 1 dimension, it's only length. It's a line. It's a straight line, and its measure is just a length. A longer line is just bigger object in 1 dimension. Okay. Finally, 0 dimension is a point. It reduces down to a point, and then there is no measure. A point has only its location. Point is just here or there, but it does not have any length, area, or volume. That's just mathematical definition. A point has 0 length. You may go the other way. Like point, if you collect infinite points, you can make a line. Then it may have a length. And if you accumulate line, like then you have a square which has area. And when you like accumulate like planes, then it becomes a cube. Like paper, a thin paper is 2-dimension, but a book is 3-dimensional, right? It has the thick. So in this way, so I started from comparing, like at the beginning of this chapter, I explained the difference between point and line. But line is not general enough. I pretended as if the probability is proportional to the length, but length is not general enough. We have to introduce 2-dimension area. So from now on, I am going to measure probability as an area. Okay, let's see. This is how I'm going to do. Now we have another dimension. Previously it was just one line, but now we have another dimension, like a height. So we are going to have, and we think of a function defined on this straight line. You have a function like this, like step function, like that. Then we are going to define probability on an interval as the area on the interval below this function, like this, right? Basically, this is the same shape, right? And if you are interested in the probability between 11.9 and 12, you have to calculate the area here on the interval below this function. And you know, the width is 0.1, height is 2.5. If you like, then the area of this square, the rectangle, is 25%. That is how we calculate the probability. Similarly, if you would like to calculate probability between 12 and 12.1, now it is this square, this rectangle, right? So now here the width is the same. Like these two rectangles have the same width, but height is different because it is higher here than here. So this area is 30%, which is the probability between these 2 points. So you may calculate probability between 11.9 up to 12.1. It is just this area plus that area. That's how you calculate the area. So that's how you calculate the probability. The answer is 55%. Okay? It's pretty interesting. So when you see, even if the widths are the same, still the height determines the probability on that interval. And where the height is high, where the function is higher value, has a higher value, there are more probability. It's say low here, the function value is low here, that means it's not likely to happen here. A little higher value, the higher value, and then the highest value. So most of the probability is happening here, like most likely and least likely, right? So the height can differentiate the probability at different points. We call that as the probability density function, right? It is density, like when the function has a higher value, there are more denser probability. Probability is denser in this area because within the same length there are more probability, right? And least dense area is here. It's like population density. Within the same area there are more population, then we say it's dense. Like within the same length there are more probability, so probability is dense here, and we call that probability density function, which is denoted as lowercase f, right? And as you just saw, this function is probability density, right? This is probability density function in our example. So we use the density function to calculate the probability as the area under the curve. So the area under the density function is the probability. And of course it should be always non-negative, but it may exceed 1. As you see, the height could be 3 because you are going to multiply 0.1. In the end, you are going to multiply 0.1, so the area itself, in the end, the area, sum of the area should be 100%, should be 1, but the function value, the height, does not need to be smaller than 1 because it's relative. Like after multiplying the width, it should be less than 1, but not the height itself. Okay. Then there are different forms of density functions. Like different distribution has a different continuous distribution has different density. Uniform distribution is uniformly dense, like from between like 1 and 4, right? And there is no probability outside. So if the value is density is 0, that means there is no probability there. And exponential distribution, for example, has the peak at 0, but the density decreases. This is unlikely to happen as the outcome increases. Gamma distribution is a weird distribution, peaked at 1 at some point, like increases, like peak at 1 and then decreases, right? Finally, normal distribution. You must have heard about this. Bell curve. This is the bell curve. It's centered around 0 and symmetric. Okay? So, different distributions have different density, like if the randomness is continuous. Okay? And area between the probability between 1 and 2 is this area. Like if you are interested in probability between 1 and 2, uniform distribution has a rectangle, so easy to calculate. But exponential distribution, it is not a triangle nor not a simple way, not a simple shape to calculate the area. Similarly, gamma distribution, it is like a little curved here, but anyhow, the area, colored area is the probability between 1 and 2, depending on which distribution you have. Okay, so that is how we handle the continuous random variable, right? And if you are smart enough, you must have realized that what I just showed you is basically a integration, right? So orange area is probability between 1 and 2, and that is, if you think about this function, this area is the integration of this function between 1 and 2, from 1 to 2, right? Similarly, the green area is the area between 3 and 4 below the function. That is integration of f from 3 to 4. So it is just an application of integration to probability, right? But I'm not going to use integration anymore. I just point this out here. The connection between probability and integration. Anyhow, they are areas, some kind of areas. So that's all the calculus knowledge I'm going to ask for you. Anyhow, summary so far. Continuous random variables have uncountably many outcomes. So one point cannot have any probability. Therefore, we have to think about alternative approaches using based on like a inequality or area. So when you think about inequality, we start from the cumulative distribution function defined by an inequality. Okay? And we learned cumulative distribution function tells you different forms of probability. Okay? Another alternative is probability density function using integration or using the area, right? Basically, they are the same thing. So if you differentiate CDF, then you are going to get density. So that's if you're familiar with calculus knowledge, they are related, but they are closely related, but they are just different ways to motivate the statistical approach to continuous random variable. Okay. So I spent a lot of time to introduce a continuous random variable because it is so important, so different, and so counterintuitive to what we usually think about. So up until chapter 5, all we handled was pretty simple because they were not continuous random variable. But now on, you have to expand, generalize your way of thinking to continuous random variable. Okay, in the next video, I will start the normal distribution. So normal distribution is, of course, a continuous random variable. So we are going to start how to think about CDF and PDF of a normal distribution. See you there. Bye.